Okay, so good morning, everybody. So yesterday we were discussing how to apply a neural network, how to develop an application using a neural network. So we first do a feasibility study. That is, we first ask, do you really need a neural network for this problem? Because if it is too simple, you may not need a neural network. So because what a neural network does is learn a mapping between input vector x and out, which is from n dimensions from Rn, and output vector y, which is an m-dimensional vector. So it's learning a mapping like this. Now, suppose it's actually a linear transformation, which can be modeled by y is equal to wx, and you don't need a neural network. So you need to make sure that it's a problem is hard enough that it warrants use of a neural network. Then is it an input-output problem? So that is obvious. Then you should be able to identify what is the input and what is output, and also be able to represent that input and output in terms of vectors of fixed dimension, and need to make sure that from a physics point of view or from a mechanistic point of view, are the inputs and outputs related in a deterministic fashion. So like I said, you cannot relate some sunspot activity with some stock values and things like that. So for all this, you need a lot of domain knowledge. So although we consider neural network as simply an empirical kind of a curve fitting tool, you still need a domain knowledge to be able to develop a good model of the underlying function, right, that is given by that is indicated by the data. So you can never overemphasize the value of domain knowledge, because you can use domain knowledge to break up the problem, right, and map problem onto neural network. You can also use domain knowledge to guide how to collect data, how much data must be collected, right, in which class, how much data must be collected, all those things. For all those things, you need domain knowledge. And even for data processing, how to represent the data as input to the network, for that also you need domain knowledge. Because basically what is happening is in a neural network, you take some data which is passive and give that data an active form. The data is a bunch of an x's and y's. Okay, and you are making this data into an active form, so that in this form the network will be able to actively relate. Given an x, it will be able to give a y. Therefore, a neural network is only as good as the data with which it is trained. Right. So if you want to come with an effective model, you need to have an effective or a comprehensive data set. It should be used to train the network. So the data must be abundant. It must be, ideally real data, but usually it's hard to get enough real data. So very often, in a lot of cases, people combine some real data with simulated data. The simulated data is just basically to kind of uh, increase the flesh, increase the volume. Right, real data is to make it more reliable and close to the reality. Data must be comprehensive in the sense you should include all possible cases. Right, suppose you are trying to recognize numbers. Okay, so handwritten numbers. So you take examples from, you give a image of a number and you should be able to say what is that number. Now, if you train it on 0, 1, 2, 3, 4 and test it on 5, 6, 7, 8, it won't work obviously. So you need to make sure that all possible cases of the data are represented in the input data. And the data must be reliable, so make sure there are no errors, or at least minimal errors. And then the representation is quite important. Now, how do you represent the data? So this is where some domain knowledge is becomes useful. So let me give you an example. So let us take the problem of odd versus even discrimination. So suppose I give a number, right? You need to train a network or design a network which can classify. So this is a neural network which can classify it into odd or even. So this is a two-class problem. So now you need to represent the number as a vector, right? How do you do that? So suppose I have number like 327. Okay, let's say I'm confining myself to only three-digit numbers. So then each of these positions, digit can take 10 different values, 0 to 9. So maybe I can represent that as a binary vector. So 0, 0. So 7 would be 0, 0, 0, 0, 0, 0, 0, 1, 0. Yeah, this could be the 7. And similarly, 0, 0, 1, etc., up to 0 is 2, and so on. So you can define each of these, you can represent each of these digits as a 10-dimensional binary vector, and you can then concatenate all these three vectors and train a network. It will, and if you have enough number of cases, it will be able to learn this, might be able to learn this odd even classification, right? So there is a natural way to approach it. But just imagine, so this is in decimal system. I'm using the familiar decimal system. Instead of decimal system, I use binary system. So this way also I can represent the numbers as vectors. So I take 327 and represent it as a big binary vector. Now the classification into odd and even becomes trivial, because if it is an odd number, the last bit will be 1. Okay, and if it is an even number, our last bit is 0. Right. So no matter, so all the other bits you can ignore. So classifying the number in this case into odd and even becomes trivial. You just have to play with the weight of the last bit. So thing is, to figure out that fact, you need to understand the numbers, you need to understand number systems, and you need to have domain knowledge, right? So with the proper domain knowledge, you'll be able to design the correct representation for a given problem. So similarly, you need to remove irrelevant or redundant information. So suppose in some cases you take some lots of parameters, some 100 parameters, and then later on you find that among those parameters, lot of parameters are simply scaled versions of each other. Okay, so there's no need to have x1 and 3x1 and 5x1 and 6x1. It's unnecessary. So remove all the other redundant variables. So similarly, you can normalize so that if numbers are not very big, right, and scaling so that all the input variables have about the same spread. So suppose x1 is in the range of some 0 and 1, and x2 is in the range of some 10 to 10 power 5 or something like that, right? So then what happens is the input data in the x1 dimension you have very small spread, right? In x2 dimension the spread is very high. So what are your input data will start looking very very long, right? And so that kind of data is harder to classify. So what people do is to make sure that all the input variables have about the same spread, so that it's of this kind of a elliptical looking distribution. So you'll get more spherical looking distribution, right? And so similarly, reduce input dimension. So when you have large input dimension, okay, so when you have large input dimension, you need more data to fill the input space, because suppose I have only one dimension and it is from 0 to 1. So this is 1D. And let's say my resolution is 10 points per unit interval. So I just need 10 points, 10 data points for this. But same thing if I take a 2D data, right, from a unit square, right, then I take 10 points from each dimension. Okay, so that will be 100, right, 100 points. So basically your number grows as 10 power n, right, where n is the dimension. So your number of points that you require to fill the input space at a given resolution increases very rapidly with the number of input dimensions. So it's preferable to use as small input dimension as possible. Okay, so for that, people do what is called dimensionality reduction. And one method for that is PCA. I'll try to cover this towards the end of the course if there is time. Other thing is people also extract features, right, which are specific to the given domain, so that it will be easier to learn the classification. So once you have data like that, then the next question is how to train. So for that, first you need to choose an architecture. Right, what kind of network will you use, and will it have one hidden layer or two hidden layers or 150 hidden layers? Because in these days of deep networks, people are using networks with very large number of hidden layers. Then first thing that you do once you decide on the architecture is to initialize all the weights. Usually in case of MLP, it's very simple. You just initialize all the weights randomly between some kind of a negative value minus epsilon, right, 2 plus epsilon, where epsilon is some small, okay, so small positive number. Then you train it. You can train it using backprop. So when we talk about architecture, if it is a feed-forward network and if it is an MLP, then we know how to do it. There are also other kinds of feed-forward networks like the RBF network, and there are also hybrids which combine RBF networks and MLPs and so on and so forth. But anyway, so in case you are using an MLP, then you have to decide how many hidden layers, is it one, is it two, and so on. Sometimes you also have specialized architectures, customized architectures, depending upon the problem, right? Especially if you are doing brain modeling, you may want to design specialized architectures which is suitable for that phenomenon. So maybe not next class, but in the class after, I will talk about some of the work that we are doing in this area. So we want to develop a model of reaching. That is, how does the brain control the hand so that the hand reaches target. So this is the hand. Okay, and let's say this is a hand. This is a target. So how do you give it a command to reach? And the input to the network will be like a let's say the image of the target. So that will be two retinal images, like two images that you see on your eyes. Okay, and that is given to the brain. Now, brain is is like it has two hemispheres, right? Now think of this as two hemispheres. So this is the brain, and this information goes to the brain, and brain sends commands to two hands. Now, if you want to model this using an MLP or a deep network, then you need to first make sure that the network has some kind of a correspondence to the real brain. And one main important feature of the real brain is that it has two halves, a left and right half. It has a bilateral symmetry. So therefore, the network cannot be like this, the way we have been using MLPs. But you need to split it into half in the middle and make sure there are two halves like that. And that itself is not enough because even though there are two halves in the brain, the two halves are coupled, okay, in certain fashion. So you need to have some cross connections, right, between one left to right and right to left. But only thing is the cross connections are fewer in number than the connections on the same side. Okay, so that's why there is this kind of hemispherical structure. Now, how do you design a network like that? So basically, if you are just looking at artificial applications, you can use generalized architecture. But if you are looking at applications in brain, right, in computational neuroscience, you may want to consider specialized architectures depending upon the anatomy of the part of the brain that you are trying to model. Okay, we'll talk about more of this later when we study this problem. Then comes to training. So you come to training, then you can use backprop algorithm. Now, backprop, like I mentioned before, it's a slow learning algorithm. There's a lot of criticism about that. There are also ways of speeding up learning. So, for example, you can use adaptive learning, right? So basically, we are doing gradient descent, right? And gradient descent, this is your error function, and this is some weight parameter, WI. Okay, so right now, let us say you are here. Here, the gradient is negative. The gradient is positive. So you decrease, right, the weight value. Now, how much you decrease depends on your step size or eta. Okay, so if eta is very small, you move in very small steps, right, like that. If eta is too big, let's say eta is so big that in one jump I go all the way. So I want to go towards the minimum, but my step is so big that I go to the other side. So then next jump I go like make another big jump and go here. Next jump I go here. So what can happen is instead of progressively reaching the minimum point and staying there, there's a danger of flying away from there and the learning process becoming unstable. So eta very big means it can cause instability. Eta too low can give you slow training. So what do you do? So obviously there is some kind of an optimal eta. And that optimal eta is generally right different at different time, different stages of learning. So usually you start with high eta in the beginning of training, and as you approach the solution, as error change in error the rate of change in error becomes smaller and smaller, right? You use so later on in training, you use smaller eta. So there is a way of adjusting eta constantly as learning proceeds, depending upon how your error is changing. So that is called adaptive learning, right? So lots of methods for that. And there's also something called momentum, so that you can speed up learning. Then there is something called an higher order method. So because what we are doing in backprop is a gradient descent, where the change in the weight depends only on the first derivative, dou E by dou Wi. So this is a first order method, depends only on first derivative. So similarly, there are also methods where the weight change depends on the second derivative. Okay, so there people use something called Hessian of the error. So it is dou square E by dou Wi dou Wj and so on and so forth. Okay, so these methods are more complicated. They're more computationally intensive, but they can be faster, right? So I don't want to go deeper into that. Then so you can train networks like that. You can have fast training. Now, when do you stop it? So stopping criteria is very simple. If error is less than some minimum value, okay, stop. So that is one criteria. But sometimes if the network is not, let's say, large enough, or your data is too complex, then error might never go to very low values. So then what you do is, so what can happen is, you can start at a very high error, right? And and just error might just go down a little and flatten out very quickly. Whereas ideally I wanted to go to such a low value epsilon, but it might never go very low. Then what you do, if you're waiting for it to go to this value, it will never happen. It will keep on running. So then what you do is look at the rate of change of error. And if that is less than some epsilon, so I'll call it epsilon 1, call it epsilon 2, right? And then you stop. So this is one way. But there is another way which tries to improve generalization. So I'll come to that in a minute. So for that, what you do is, so usually when you train, right, your training error, that is the error on the training data, keeps on going down because you are learning that data more and more with the network. But if you simultaneously take a test data also and look at the performance on test data also simultaneously, then what will happen is the test performance will be slightly worse than training performance because test data will be different than training data. So obviously it will be worse than training data, training performance. And test performance also will be improving, or test error will keep going down. But what will happen is beyond a point, the pattern of variation in test performance, pattern of variation in training performance begin to diverge. That is, as you keep on training the network, the training error will continue to go down, right, and flatten out beyond a point. But the test error might start increasing, right, beyond a point. So this is where you come to the idea of generalization. So that means the network is basically mugging up the data. It's just memorizing data, not looking for underlying patterns. So therefore, it is doing badly on the test data. So this happens even, if you take an analogy from the way you prepare for exams, right? If you want to do well in exams, you have to learn your tutorial sheets, all the problems in tutorial sheets you have to solve and get an understanding of the concepts. But if you mug up the problems in the exercise and tutorial sheets and expect to get the exact same problem in the exam, and start giving the same answers in the exam, even though the exam questions are slightly different, then obviously you start doing worse in the exams. So this is something like that. Beyond a point, if we just keep on beating the network to do better and better on the training data, right, it will start performing badly on the test data. So therefore, to understand where the network has crossed that point, you look at the error, test error and training error simultaneously, as right, at various points in the training, various stages in training. And whenever the test performance is diverging from training performance, you stop training. So this criterion for training is called early stopping. Okay, that comes to the idea of generalization, because the objective of the network, although we said the objective of training is to minimize the training error, but you pushing it excessively to reduce the training error too much is also not a good idea, because the ultimate objective is to make sure that the network does performs well on an independent data set, which is the test set. It will always do well on the training set given a network that is large enough, but ultimately the real test is how does it perform on a test set. So to understand that, let us look at this kind of a Venn diagram. So U represents the universal set of all possible training pairs, all possible input-output pairs, XY pairs. Now within that, I'm trying to learn one set of XY pairs which are represented by a function. So let us say my input function y is equal to some sine x. Okay, so over some interval x is between 0 and 2 pi or something like that. So this is my function I want to learn. So this function represents a bunch of specialized xy pattern, xy pairs. So this ellipse, let us say, represents that function. This ellipse. Now we don't know the function, so we cannot just tell the neural network, okay, go ahead and learn this function. So because all that you have about this function is a bunch of xy pairs. So if x1 is the input, then the corresponding output is y1. If x2 is the input, corresponding output is y2, and so on. And not only that, you also have some noise, because if it is a physical process, right, you are likely to have some noise, so u1, u2, and so on and so forth. So all that you have is this, right? And this noisy data, and also you may not have data from the entire functional space, right? Data could be slightly scanty. So your training data might represent only a part of the function, and that could be represented by, in this Venn diagram, by this circle T. This is training data. So what you are saying is, so my original function is f, right? This ellipse, and within that I have data which only represents a subset of that, and that is this T. Now, based on this, you expect the network to learn the overall function, which is given by the ellipse, and in that way, it should be able to do well in this another subset, right, which is the test set X. Okay, so this is a tall order, because so what can happen is network doesn't know F. It is trying to guess what is F indirectly by looking at the training set T. Now, if you push the network and train it very hard, it might generalize beyond T. That means it will learn to map other input-output patterns. But that learning could be like this. Okay, which is totally valid. It's doing its job because you said learn all these T, and it has learned it. And beyond that point, it has also learned some other patterns. And these patterns are okay. Up to this part, it is okay because they are all still coming from the same function. But beyond a point, all these other points are not part of the function f, and it is learning some junk. And it's quite possible because it's doing what you have told it, but you have no control over what it learns in the other regions of the input space. So this is still a problem. And in this process, it hardly learned anything in the test data. So if you give the test data X, it will do very badly. So this is always a problem. So let me give a simple example to illustrate this. Suppose I want to learn this function, which is just a parabola. Now it could be something like y equal to some 4 into x into 1 minus x. Now I want to learn this function. I don't have the function available, but I have only some data available, and this data also comes with noise. Okay, it's like this. So now I want to train the network. Now I use a network which has lots of hidden neurons and beat it to death, and it's able to learn. It's got like zero training error, perfect performance. Right? That means what it does is it will do very well on the training set. Okay, that's like mugging up your tutorial questions. So the network fit might look something like. Okay, so you see that it has done perfectly well in all it is going through all the points, right? It has learned even the noise. So ideally, it should ignore the noise and learn this underlying pattern, which is a parabola. But it just mucked up the noise, and since the network has so many free parameters, because it's a large network, a large hidden layer, it has too many wiggles. You see that, and so it has learned your training error is zero. You'll think you'll be very thrilled that you got trained it so well, but it didn't learn the underlying pattern. So if you give some other data set, which also will have noise, but coming from the same function, right, with the data set which looks like this, you see that it will do very badly in all that data because it didn't capture the underlying function. So this is quite possible. So one thing you can intuitively guess here is that one problem with the network is it is too complex, right, for a given problem. So you need to make sure the network is not too big for a given problem and just right in size. Okay, so suppose you use a fewer number of neurons for the network, right? You may not get a fit with so many wiggles, but you might end up with a network, I don't know, maybe something like that. Okay, which is far better. It looks a lot more like a parabola than this one. It may not give you great fit in the training data, but it's caught the underlying pattern of the unknown function. So it will do on the whole better on the test data. So this will happen only when your network size is sufficiently small to fit the data. So one good training goal to achieve, which is not easy to achieve because we can only state in somewhat abstract terms, which is that we need to be able to match the neural network complexity with the problem complexity. So here the problem is not very complex, it's just a parabolic function. So you need to make sure the network is not too big, not too complex to learn such a function. So this is there's no straightforward answer to this because there are certain mathematical requirements there, but they're very hard to satisfy. Hard to achieve those conditions. But anyway, it's important to know that this is a necessary criterion. Now, so one thing people do to make sure that this, to achieve this result, that is how to match network complexity with the problem complexity. So basically, you try to make sure that the number of free parameters is not very high. Okay, so what people do is something called regularization. So normally, what we do is we just train the output error. So half of d minus y whole square over all possible patterns. So this is so one major criteria for training is minimize output error. But in addition, right, people also minimize some kind of a function of the weights. So make sure, so this can take on many forms, but for example, make sure the modulus of weights is always as small as possible. Because if, for example, if I just satisfy only this, I'll set all my weights to 0. So that will mess up my first criterion. So there are two objective functions where there's a trade-off that is required, right? So we try to minimize both to the best extent possible, right? And so one way to do it is use f of w will be something like so sigma wi square. Okay, so here we are only trying to penalize its magnitude. We don't care about its sign. We just want to avoid large weights. Okay, so when you add this also into gradient descent, right? And so what will happen is so delta w is equal to minus your let's say delta wij is equal to eta times delta I times vj. This is what we derived in the last class. In addition, we also have this kind of a right gamma. So I'll have, let's say, 2.5 here. So gamma times wi. Okay, so you basically, in addition to your gradient descent term for the output error, you also have like a decay term, so which will try to penalize very large weights. So that is called weight decay. Then there's also one more example just to give of pruning. Is suppose you train a network, and let's say it's an MLP, and so you have lots of weights. After training, you actually go ahead and ask the question, like take some weight here. Is this weight necessary? Okay, so how would you answer that question? If I remove that weight, what happens? So what do you mean by what happens? Right, because ultimately the criterion of how good the network is it can be captured by the error function, the output error function. Okay, so which is sigma over patterns half of d minus y whole square. So I want this to be a minimum, to be small, right? How do you know this weight is important? If I set this weight to 0, so this is some wij, if I set it to 0, will there be a drastic change in this error? That is, obviously, most likely this error will increase if I randomly take some weight and set it to 0. Now, will it increase first of all? And if it increases, by what extent will it increase? So the original E, okay, so take set some wij is equal to 0 minus EW, the original weights, right? This quantity I'll call this delta W, right, for the ijth term. Now, sorry, delta E for the ijth weight. How big is it? So depending upon that, I can decide whether I can throw away the weight or not. So actually the criteria is even more complicated than this, but I'm just giving an idea. So applying such criteria, I can actually toss weights. I can throw away weights and come up with a much leaner network. And like I said, so the network complexity lies in the number of free parameters that are available in the network. So if I can throw away weights, so then the network is likely to generalize better. Now, pruning connections happens in the brain all the time. Only thing is we cannot say that it's happening because it wants to achieve better generalization. But throwing away of connections is happening all the time in the brain. Okay, so that is some basics about how to design the network, how to train the network, how to collect the data, and so on. So let us look at a couple of examples. Now, we can give real-world examples from engineering examples. We can also look at applications of network in psychology, in neuroscience, and so on and so forth. So in this class, I'll present a couple of examples which are slightly artificial, but which have some kind of a biological or a neuroscience flavor. Next two classes, we'll look at slightly more interesting, deeper models of simple MLP or a deep network to problems in neuroscience. So like I said, when MLP and backprop algorithm were first discovered in the 80s, people quickly applied these new network models to lots of problems in psychology, cognitive science, just to show that you can explain a wide variety of phenomena in cognitive science, linguistics, and psychology, and things like that, using these very simple network models. Because the nice thing about new networks is they're very general solutions to a large class of problems. Okay, so that was what was quite appealing about them, and it created a big excitement right, way back in the 80s when they were first discovered. So in this paper, Rumelhart and McClelland, they study how children learn past tenses of English verbs and how you can capture those patterns using a neural network. In fact, they just have taken a perceptron. It's not even an MLP. And even that can capture some of these patterns of learning that you observe in real children. So apparently, when children learn English past tense forms of English verbs, you see three stages in their development. So in the very first stage, they have very young children. They have a small vocabulary, so they only know a small number of verbs, right? And these are typically commonly occurring verbs or high frequency words. And so in the past tense, you have two kinds of past tense forms. One is irregular, other is regular. The regular one is one where which we encounter most often. It has the ed ending. Okay, look and looked and need and needed and so on. The irregular ones don't have ed ending, but they have some random variation. Okay, come and came, got and give and gave and so on and so forth. So these are some of the commonly occurring verbs, but most of them are irregular. Not so. This is regular, but this is irregular. Go and went is totally disconnected, but so that's irregular and so on. Now, in the second stage, the kids will have greater vocabulary. So they'll start using a lot more words, and a lot of them are regular now, like wipe and pulled and so on. So, but what happens is once they are exposed to this large stock of verbs with a regular ending, they start messing up their past tense of the verbs which they've learned in the first stage, right? So all these irregular verbs, irregular past tense cases, they start messing them up and start wrongly applying the regular ending to the irregular verbs. So, for example, they might say come, the past tense for come, they might say as comed or came, right? Both are wrong. So, this kind of an erroneous substitution can occur in the second stage. And third stage, now they're able to resolve this confusion. So, they are able to understand that there are two different kinds of past tense forms. One is irregular, so you have just basically memorized the past tense form. There's no rule there. And then there is a regular case where you can use the ed or just d ending. Okay, they can resolve this confusion and they don't make mistakes in the third stage. Now, how do you capture this? So people who have known this phenomenon for a long time, and people have studied this and tried to account for it by proposing all sorts of complex theories of learning and grammar and so on. But whereas when you apply this to a neural network, a very simple neural network, a perceptron, they found that the perceptron makes exactly the same kind of errors, right, as it is trained to learn past tense. So how does it work? So in this case, the perceptron is trained in three stages, and for that they have taken different sets of verbs. So they have taken 10 high frequency verbs. These are the commonly occurring verbs. Among them, 8 are irregular and 2 are regular. These words are, came, get, give, uh, take, go, have, feel, look, live, right? And then there are 410 medium frequency verbs. Among them, 334 are regular and 76 irregular. Then there are 86 low frequency words. These are among them 72 are irregular and 14 are irregular. Okay, in stage one, they have just used the 10 epochs of the high frequency verbs, these 10 verbs, right? And 10 epochs turns out to be enough to get good performance, good output performance. So in the network, they give the original verb, right, and original verb as input, and its past tense form as the output. So there is some way, convention by which you can present words as vectors. So I'm not going to all that. So they have worked out that convention, explained that in the paper, but I'll skip that. So they take this 410 medium frequency verbs, and then they also add the first set of 10 high frequency verbs, which they've used in stage one, and combine them and train the network on this combined data. And this training occurs for 190 more epochs after this 10 epochs, and that is the stage one. So that is stage two. So then in stage three, there is no further training. They just take these 86 low frequency words, which have some irregular and some regular, some irregular, and just test the network performance. So what they found is beyond stage two, right? The performance of regulars and irregulars is nearly the same, and each touching very close to 100%. And the performance actually looked like this. So this is the number of trials or epochs, right? And so you can see that at about 10 epochs, which is around here. So it's right after that when they started the larger stock of words with 410 medium frequency words. They started the performance has been continued to improve on the regular verbs because in 410 most of them are regular, and so it's able to generalize that underlying pattern. But in the second stage, it's also being tested on not only this 410 medium frequency, but also the 10 verbs on the first stage, which have mostly irregular. So the performance on the irregulars suddenly started dipping. So it's making mistakes on the irregulars, which and it's going worse than what it was doing in stage one. At the end of stage one, it reached this point right? It was doing fairly well on even on the irregulars. But once it got exposed to regulars, it started generalizing on the lines of regulars with the ED by adding the ED ending and start messing up the performance on the irregulars. But as you continue training the network, so after about, because second stage is training goes on for about 190 epochs. So after 200 epochs, you see that performance on both regular and irregular has reached a very high value. Both are very close to, way above 90%. Then let us look at another network, which is called the convolutional unit. So some of you must have heard of the convolutional unit networks. They are very popular now after this deep learning revolution. But actually, they are very old. I mean, they were proposed first in the late 90s, and they became again more popular after the deep learning stuff has begun in the 2005 2006 period. It was first developed by Lacoon, a guy called Lacoon, where this guy and his group have applied this network for reading handwritten numbers. So handwritten digits, right? Because they did as an application for AT&T, and which was a application which was done as a project for U.S. Postal Service to read the zip codes or pin codes written on the envelopes of that. So this is inspired by the biological visual system because it's not a simple MLP, but it is a special architecture which is more tuned to image pattern recognition. So it looks something like this. So you have the input image is given here as a 2D array because it's an image. And then the hidden layers are also 2D arrays. Because the regular MLP is simply a bunch of 1D layers. Okay, and in every layer, every neuron is connected to all the neurons in the previous layer. So that is how the regular MLP works. So these are called, such layers are called fully connected layers. But in case of convolutional network, it is different. So the hidden layers also up to a point are actually, they consist of multiple two-dimensional arrays of neurons. And a given neuron in each of these 2D layer, right, is connected not to the entire image in the previous layer, but only to a small part of the image, like that. So this neuron is only connected to the small window of neurons in the previous layer. So similarly, if you take a neuron here, right, it might be connected to only a small array here, right, but it will also be looking at a similar array in the other 2D arrays. So by the way, these arrays are called feature maps. Okay, so there is a very specialized architecture. So because original MLP has all-to-all connectivity, every layer is connected to every neuron in the next layer. But here it is all the connectivity is local. And this pattern goes on up to a bunch of hidden layers, right? And after that, they all project to one-dimensional layers, and from that point onwards, it has full connectivity. So we'll discuss more of this in future classes. But this kind of a specialized architecture is good for image pattern recognition, and it was giving very good results. So one thing they found, which was very surprising about the performance of the network, even in these very old versions of the network, is it was trained on regular data, right? Like handwritten data, like 0, 1, 2, 3, and so on. The data was quite messy, but it was able to learn well. But what was interesting is once the network was trained, it was given these kind of a shady, complicated, or pathological examples. So they made some synthetic data just to confuse the network. So 2 was written, right, for example, in like this with lots of small circles. And obviously nobody writes 2 like that, but it was designed just to confuse the network, but was able to recognize the network, recognize the pattern very well. So it got this 2. Similarly, 4 is given as a hollow 4, right? There's nothing in the center. So it was able to recognize that. And similarly, 6 was given with a lot of broken segments in its contour. It was able to recognize that. And there are also other cases. If you go to this website, you can see all these strange cases where they had multiple numbers appearing in the same window, and these numbers could be moving, they could be stretched and scaled, and in spite of all that, network is able to recognize the numbers correctly. So it's almost generalizing very naturally, and it's showing kind of expertise which you would expect in a human visual system, not in a simple, in a machine, in a artificial system. So that was a big achievement in those days, back in the late 90s. So more examples. 3 is given like this, 5 is given like this, and 8 is given as two disconnected circles, right? Which is obviously quite bad, but it's able to recognize 8. And look at all this stretching and pulling and moving. It's able to recognize, right, in this case, the 3 numbers. So let us stop there, right? And so next class, I'll present a few examples of how an MLP, actually, now I'll be talking about deep networks. We'll look at how deep networks can be used to understand some phenomena from real nervous system. Thank you. So any questions?